Hello and welcome to the video lecture on delay calculation in 8051 assembly. First we will understand what is the meaning of instruction cycle and machine cycle. The time which is required for completing the execution of an instruction is called as the instruction cycle, and the CPU takes certain number of clock cycles to execute an instruction, and these clock cycles are nothing but machine cycles. The length of each machine cycle depend upon the frequency of the crystal oscillator, which is connected to the terminals X1 and X2 of 8051 microcontroller. Normally we use a crystal of 11.0592 megahertz because this crystal make your 8051 compatible with the serial port of IBM PC. So in this video, I am using the clock frequency is equal to 11.0592 megahertz. If we consider the original 8051 version, the one machine cycle lasts for 12 oscillator period. And if we consider the clock frequency of 11.0592, then we can calculate the time required for one machine cycle, which is as shown below. So first you have to take the crystal oscillator frequency and divide it by 12. So which will give us a frequency equal to 921.6 kilohertz. And here we are interested in calculating the time period of one machine cycle. So you have to take the inverse of this frequency. So 1 divided by 921.6 K, which will give us 1.085 microseconds. But if you go for the other versions of controller, then you will find that the number of machine cycles required, or for one machine cycle, the number of oscillator periods which are required are different. So if the controller is different, then you have to consider that value. This we are discussing for original 8051 microcontroller. So these are some instructions, their machine cycles, and the time to execute the instruction is given in this chart. So the move instruction will take the one machine cycle, and therefore 1 multiplied by 1.085 will give you 1.085 microseconds time period. Similarly, DEC instruction also takes one machine cycle. DJNZ require two machine cycles. L jump, S jump also needs two machine cycles. NOP takes one machine cycle. So these are the examples that I have shown you for calculating the time for execution of these particular instructions. Now we'll see one example how to calculate the delay size in the below program. Now this is a program in which we are going to toggle the port P1. So we are going to load the pattern 55 and AA, and we are calling a delay in between. So first we will decide what is this delay size. So for that, let us consider this part. This is our delay routine is. So there are three instructions. The first instruction is move R3 comma hash 200 DJNZ R3 comma here and return. There are three instructions. So whenever you write any delay in delay calculations for assembly, you have to consider two things. First is you have to set some counter, and you have to decrement that counter. That means you have to use a loop. So setting a counter and using a loop, these are two important things in writing a delay routine. Now here the count value which is loaded is 200. So therefore this DJNZ instruction will get executed 200 times. So first we will see the number of machine cycles which are required for this all instructions in the routine. So just now I have shown you that for move instruction it takes one machine cycle. For DJNZ it requires two machine cycles. So I will write here the machine cycle. So this is a one machine cycle. It requires two machine cycle. and return also take 2 machine cycle. When we calculate the delay size, then actually we have to consider the instruction which is inside the loop. But if you take the instructions which are outside the loop, you can go for the more accurate delay calculations. So now in this case, this DJNZ instruction requires 2 machine cycles and it is executed 200 times. Okay, so now I will show you the calculations. So 200 multiplied by 2 plus move R3 comma hash 200. This instruction is executed only one time. It is going to load your count value into register R3. So the machine cycles required is only one, and return instruction is also going to execute only one time, and the return instruction also takes 2 machine cycles. So total number of machine cycles required to execute this delay is 400 plus 3, which is equal to 403. These are the machine cycles. Now if we want to calculate a delay, time delay, then in that case you have to multiply this number of machine cycle with the time period of one machine cycle, and the time period of one machine cycle is 1.085 microseconds. So in my previous slide I have already shown you this, because we are considering the crystal frequency of 11.059. So after multiplication you will get some particular delay value for this routine. Okay, so this is what is the single and the simple loop that we are going to uh, write if we want to generate a delay routine. Okay, so let us check this value, what it comes out to be. So this value is 437.255. This is 437.255 microseconds. Okay. Now I will show you one more example how to calculate the delay size. Now this is the loop inside loop delay, which is also called as a nested loops. So in this case also we can calculate the amount of delay that is generated. So here, as there are two loops, first we will only focus on the inner loop. So first we will consider only this loop and we will calculate the delay time for this inner loop. So as this control is here, I will call this loop as here loop, which is my inner loop. So first we will calculate this. Now here move R3 comma hash 250 is nothing but a count value which is loaded into the R3. There are two NOP instructions and the last instruction is DJNZR3. So this instruction NOP, NOP and DJNZ, these three instructions, they are going to execute 250 times. The NOP requires one machine cycle and DJNZ, we know that it requires two machine cycles. So what is the delay over here? So 1 plus 1 plus 2 multiplied by 250. This is what is the number of machine cycle for this inner loop. So which comes out to be 2 plus 1 means 4. 4 into 250, which is equal to 1000. So these are machine cycle required for inner loop. Now we'll consider this outer loop. Now in outer loop, the R2 or the count value loaded is equal to 200. Therefore, this move R3, NOP, NOP, DJNZ and this second DJNZ, these all instructions are going to execute 200 times. Okay. So, first we will calculate the number of machine cycle for the outer loop. So, outer loop calculations. So, in this case 200 into this move R3 require only one machine cycle. So, 1 plus NOP, NOP and DJNZ, these three instructions, they require 1000 machine cycles. So, I will take it as it is. Plus this DJNZ requires 2 machine cycles. This plus 2. Okay. And I will add this move and return. That means one machine cycle for this move and 2 machine cycle for this return. So these are total number of machine cycle to execute this entire delay routine. So this calculation comes out to be 1000 plus 3 into 200. So 200 into 1003 plus 3. So 2 zeros, 3 to the 6, 0 0 plus 3. So how many number of machine cycles? 200603. These are number of machine cycles, and therefore the delay is 200603 multiplied by 1.085 microseconds. So which comes out to be 217654 microseconds. So nothing but 217.65 milliseconds. So that means if you want to generate the larger delays, you have to go for the nested loops. Okay? So these are two examples, but see, whenever you write a program, then actually you have to set this count value. So what is this count value? For that there are some steps required. So now we'll uh, do some calculations for these steps, and how to decide that count value, that we will see with the help of some examples. So let us consider this first example, that is generate a delay of say 50 microseconds. Okay, so now I will show you what are the different steps. The first step to decide the delay size is this given value, that is a 50 microseconds, you have to divide it by a time period of one machine cycle, so that you can first get the number of machine cycles. So this 50 microseconds divided by 1.085, so which comes out to be 46.08. So value is 46.08. But if you see, the main instruction which is causing a delay in this is DJNZ instruction. In loop, the important instruction is a DJNZ, which is responsible for generating a delay. And this DJNZ instruction requires two machine cycles. Okay, so you have to divide this count value, that is 46.08, divided by 2. So it comes out to be 23.0. So what count value you are going to load for generating a delay of 50 microseconds is 23. So using this value, now you are going to write your delay. So now how to write a delay? So in this case, first I have already told you that you require a counter value, and second important thing you need is a loop. So first you load this count in any register. So let us consider R2 register and load this count value, and just use DJNZ instruction and use a loop and give the control over here and return. So this is the simple delay routine for generating a delay of 50 microseconds. Now here you remember that these registers in which you are going to load your count value, they are all 8-bit registers. Okay, so the maximum value that you can load in this register is 255 in decimal. So that is a maximum value, and using this value you are going to generate some maximum delay. Okay, so if you take this value equal to 255, then what is the maximum amount of delay that you can generate using a single loop? So let us see what is that value. So if we write move R2 comma hash 255 and use a DJNZ instruction and return. So let us calculate the delay size. So this is 255. So DJNZ will be going to execute 255 times, and number of machine cycle required are 2. So 255 into 2 plus 1 for this move and plus 2 for this return, because both these instructions are going to execute only one time. So 255 multiplied by 2 will give you 510 plus 3, that is 530. So this is the total number of machine cycles multiplied by 1.085 will give you the delay. So let us calculate, will give me 556.605 microseconds. That means the meaning of all this is, if you want to set a delay up to this point, that means up to this value 556 micro, then you can go with this single loops. Okay, but all of we know that we also need the delays in milliseconds and seconds, right? And therefore in that case we have to go for a nested loop. You may have to use 2 loops or 3 loops. So now let us understand how to calculate the count value for larger delays. So let us consider one more example for that. Now let us consider this third example. That means suppose you want to generate a delay. Okay, first we will take for milliseconds value and then we'll go for this. So let us consider if you want to generate a delay of say 0.5 milli, but 0.5 milli is 500 micro. So again that will do your job with a single loop. So I will consider a different example. So let us consider that suppose I want to generate a delay of 10 milliseconds. Okay. So what are the steps for calculating the delay of 10 milliseconds? So as I have explained you, for 10 milliseconds delay, first you have to divide that particular value by 1.085. So this 10 milliseconds divided by 1.085 microseconds. Okay. So this count comes out to be 9216.58. And whatever is this count, that is 9216.58, divide it by, okay. So after dividing it comes out to be 4608. But if you see, this count value is greater than 250. Okay, so you have, the meaning of this is you have to go for using multiple registers, that means the nested loops. So one way you can design like this is, you divide this 4608 by 250. So if you divide, it comes out to be 18.07. So now you have to use 2 loops, the inner loop with a value 255 and the outer loop with a value 80. So if you want to write a delay routine, then what are the instructions for this delay? So my first instruction in this delay routine will be move. Let us take one register R1 hash 18. Then you go for loading this second count, that is 250. Then use, first complete the inner loop. So djnz R2 comma here, and just give the control over here, and then you decrement this outer loop counter djnz R1, give some name and give the control over here, and finally write the return instruction. So with this, if you calculate the delay size with our previous method, you will find that you will get the delay of 10 milliseconds. Okay. So likewise, you can generate the delay in 8051 assembly. Now here I have considered, or I have divided this 4608 by 255, but you can also break this 4608 in 2 parts and you can load some different values also, that is also possible. So this is what all about the delay calculation. In my next video, I am going to show you the demonstration of the same problems in Kill. So guys, keep watching my video, and if you like the video, then please share the video with your friends, and if you have not subscribed to my channel, then please subscribe the channel. Thank you so much.